we have left last time, and we are gonna use the NumPy library to implement one of the most famous machine learning technique, which is a linear regression model or kernel regression model. Okay, so let's get started. Okay, so is my screen visible?
Yes.
Yes.
Okay, so you are seeing the Colab file, right?
Yes. Yes.
Okay, so yesterday Karthik must have covered the NumPy library, the basics of NumPy library, and how we can use NumPy library to create the data set and different functionalities of the NumPy library, which is very important and very easy to handle as well, right? So I think you all of you now must be familiar with the NumPy and how we can create the NumPy arrays and how those can be represented as a vector and the matrices, right? So any one-dimensional array is your vector, so you can think one-dimensional array as a vector and the two-dimensional array as a matrices. And by now you are very much familiar that how much matrices are important because we represent our data set in a matrix format in a vector format in the all the machine learning techniques that we have covered in MLT course, right? So today now we'll cover some of the more important functions of the NumPy library, and then we will go to the linear regression model. Okay, we'll try to implement the linear regression model using the NumPy library. Okay, so let's get started. First, let's import the NumPy library. Okay, so as I mentioned that you have in one-dimensional array will be your vector and two-dimensional array will be your matrices. Now you have also seen what is the shape, what is the dimension of the matrices and vectors and even higher dimensions arrays, right? So here, if I start with X, then how you can create your one-dimensional array? You just simply call np.array, and inside that you can pass the list, and in that you can pass how much vectors you want, how many rows or how many columns you want. If I create only one row, so it will be my one dimensional array, and if I look at the shape of this, it's gonna be just one row with three columns, right? So these are the three columns. Now if I want to create two rows, I can start a new row which will be your four, let's say 4 5 6. So this will be your uh, now the shape will be 2 cross 3 because you have two rows and three columns, right? So this is how you create a NumPy array. Okay. Now the next function that we are gonna see is that we can reshape a given NumPy array. Now if you look at this X here, X has shape 2 cross 3. Right? Now if I want to convert into a another shape of 3 cross 2, can I do that? Yeah, there is function for that, and which just you use X dot reshape and pass the shape which you want to do. Right? Let's say if I want to pass 2, 3 cross 2, then X will be your 1 2 3 4 5 6, right? So now you have three rows that I mentioned here. Take three rows and two columns. So it will be three rows and two columns. And how number will be distributed here? Look at the original X here. If you look at the X here, X was your 2, 1, 2, 3, 4, 5, 6. So elements are stored first row wise, right? So in the first row, 1, 2 will be there. In the second row, 3, 4 will be there. In the next row, 5, 6 will be there, right? So 1, 2, 3, 4, 5, 6. So now initially the shape of X was 2 cross 3. Now my shape of X has become 3 cross 2. So X has changed or not? X hasn't changed. It has created a new array, and
Sir,
you can
is this same
yeah.
as the transpose?
Not transpose. Transpose will become 1 4 2 5 3 6, right?
Yeah.
1
Sir,
4
can
2.
I see the matrix again?
So if you look at this X here,
Uh,
if you take the transpose, it will be 1, 4, 2, 5, 3, 6. But I'm just reshaping it, and in reshaping how the number distributed row wise. It means first it will distribute the elements from the first row, then the second row, and continuously. So here first it check the shape. Here I want the shape of the new array to be 3 comma 2, right? So it will take 3 rows and 2 columns, and how numbers will be distributed according to the rows. So first in the first row, 1, 2 will be there. Next will be 3 comma 4. Next will be 5 comma 6. It's not the transpose. Okay, it's just the reshaped of a new array. And now this has created a new array. It hasn't changed X itself, but has
So,
created a new array with the new dimensions, new shape. Okay,
so when do we use this?
it will. I mean, let's say you have some numbers. Let's say np dot once you have some np dot once you have, right? And you want to, you know that my dimension is 5 comma 6, and again you want to use this one but the different shape. So then you can directly use dot reshape. It's not that hard and fast rule that always this you can do. You can always recreate it, or you can use the existing one to just reshaping it. Okay. Or what if I want to do x dot reshape 3 comma 3? Will it work?
No, sir.
It will throw an error, right? Because in the original X, there were only 6 elements, right?
6 elements.
But with what if I want to create reshape it into
9.
3 from 3? It requires 9 elements, right? So while reshaping, you must make sure that the number of elements in the newly formed array is the same as the original array. It should not be different, right? Or let's say you have 3 comma 2, right? So that is compatible with 2 comma 3. Let's say you originally you have
Sir, we
6.
can reshape to 6, 1 also, right?
Yeah, you can reshape to 6 comma 1. Let's say what if I want to reshape into 6 comma 1? Let me comment it, and x dot reshape 6 comma 1. Right now it has created the 6 rows with 1 column, right? So the numbers of elements should be same. What if I use x dot reshape, and I just use 3 columns and -1? What do you think will be what will be the output here?
So it will assume
3, comma 2.
3 comma 2.
Right? So -1 says that it will automatically decide how many columns should be there, right? How many numbers should be there. So 3 means I just told X that just take 3 rows and decide how many columns should be there, right? So if you take 3 rows, as I know in the original there were 6 elements. If I take 3 rows, columns must be 2, right? So 1, 2, 3, 4, 5, 6. So one dimension I provided. Second, the array will automatically decide. Right? Let's say if I say 4 comma -1, it will work?
No, sir.
Because
No,
4
sir.
comma -1 means that columns it will decide, and I want 4 rows. There is no way in which I can have 4 rows and I can have 6 element in a matrix, right? So that is not possible. So 3 comma 2, or what if I can do? I can pass 2 comma -1. It says that take 2 rows, and it is already in 2 comma 3, so it won't create a new one. So let's say I can say -1 comma 2, and it says that take 2 columns and create how many rows that will be compatible with the number of elements, right? So -1 will automatically decide how many rows or how many columns it will take. Okay. So that's how you can make use of the reshape to create a matrices, or I mean to reshaping a matrices or a vector, whatever, right?
So what if we use -1 comma -1?
That won't work because we haven't provided how many rows and how many columns we want, right? So it
Okay.
says that at least one dimension you should specify that how many columns or how many rows you want in your
Yeah. Okay, sir.
new array. Okay. Similarly, you can convert vector to matrices. Let's say you have a X vector and you want to convert into a matrices. So now it's of the form 6, 1, and you want to convert into 3, 2. So what you can do, you just reshape x into 3, 2, right? So that will do the task, right?
So any direct option to make it as a square matrix, reshape
Sorry, any direct method to
method to make a square matrix?
square matrix.
Yeah.
So you have 6 elements. With the 6 element, you cannot make it a square matrix, right?
Okay. Yeah. Suppose if it is if it can be made square matrix, is there any option, or we need to know the one dimension by
No,
ourselves?
it's not
like
a direct
that?
matrix to make it a square one, but you can pass the number of rows, number of columns to that, and then it will do the task, right? Let's say you have this matrix x is equal to np dot array, and you have only one vector, let's say 1, 2, 3, 4, right? Now, what is the shape of this? What is the shape of this? NP is not defined.
So your screen has freezed.
Oh, give me 1 minute. Okay, yeah, now it's working. If I say x is equal to np dot array with 1, 2, 3, 4. Now what will be the shape of x?
1, 4.
We have
One.
only one rows and 4 columns. Now, if you want to convert into 2 columns too, you just use x dot reshape function and says that just take 2 rows and 2 columns, and it will do the task for you, right? It will be 1, 2, 3, 4, right? So you have converted a vector into matrix.
So
Similarly,
why are you giving double this form of list in line number 14? We just need one, right?
no, if I just take a one, it will be a just flatten
Vector.
array. It won't be a x1, 4, right? So if I just pass 1, 1, it will be your 4, 1 vector. That will be your a flatten array. It's not an.
That is a
It doesn't
vector.
have any. Doesn't have any specific direction. So you have to bring it into a one-dimensional array. That will become your
Means are
vector.
you converting this into a matrix in this form? Means
Yeah.
is
So
this
this is
X a matrix right now?
yeah. Now this is a vector. X is a vector, right?
It is matrix.
So it becomes a matrix, no? When we
A
are
one-dimensional matrix, you can call it as a vector. Now, now you have a row vector, right? There is only one row,
Mm-hmm.
so this is a vector.
Okay.
Now you can reshape it into 2, 2. That will become your matrix. Right? Yeah, it's again. I'm calling it a vector just because there is only one row. You can call it a matrix as well because it has 2 dimensions, rows and columns as well, both. So dimension wise, both are similar. This is 2 dimension, this is 2 dimensions. So, but the shapes are different for both the things.
So what is the right approach? In MLT, we learned the columns as a data point, right? Here, the moment we do it's a row. So do we always convert into column and
That
do the processing?
we'll cover into regression part. When we'll go to that part with the right convention, we'll coding as we have covered in the MLT, right?
Okay. Yeah.
We'll discuss that there. Anyway, we take a data point as a column vector or any label vector as a column vector. And the data matrix has D cross N matrix, where D is your number of features or N is the number of examples, right? Or number of instances on your data set. Right? So that's the convention that we have followed, and we'll stick to that. Right? Similarly, you can convert a matrix into a vector. Just do the reshaping part, and you are done. Okay, matrix to matrix as well, where you have 2 cross 3 matrix, you can convert into 3. You have initially 2 cross 3 matrix, you can convert into a 3 cross 2 matrix, right? And that we have already done. Now let's move to the next concept, which is additions. So in algebra, adding 2 different dimensions matrices are not possible, right? So it can I add m plus b here? arithmetic says that you cannot add two matrices whose shape are different, right? So, but NumPy provided broadcasting techniques. Broadcasting techniques means what? Now, you can think as a task like you want to add a vector to each row or each columns to a matrix, right? So what is my task here? I want to add 1, 2, 3 to each of the rows, right? So I want to add 1, 2, 3 to first row. I want to add this row as again to 4, 5, 6. So what NumPy can do? NumPy will do the task for you, right? So this broadcasting, it is called broadcasting. Let me first define the matrices and the vector. And p dot array. Now if I define it 1, 2, 3 and 4, 5, 6, and let me define b as well. B will be your p dot array, and I can define as 1, 2, 3. So arithmetic says that this addition is not possible, but in NumPy it doesn't throw any error. It just adds m is not. So here, what is happening? It adding this row to both the rows of original m, right? So if I even give one more row, let's say if I want to say 5, 6, 3, what it will do? It will add this row to all these rows, right? So how does broadcasting work? The rules of broadcasting is that at least one, you can think as at least one dimension should be same, and another dimension of one of the array should be 1. Right, so these are the rules of broadcasting. Let's say these are your two matrices 4, 3 and 3, 1, right? Or say 1, 3. So one dimension is same. The number of columns are same, right? And another dimension here is 1 here. So broadcasting says that it stretches this matrix to bring into the same shape, right? So here it is 4 cross 3. Here it is 1 cross 3. So this will stretch to bring into the same shape. The shape is 4 cross 3. So it will stretch into 4 cross 3. So it will make the copies of the first rows 4 times. 1, 2, 3, 1, 2, 3, 1, so such 3 copies it will create. Now this both comes into the same dimension or same shape, and then it will it will be added, right? So first row will be first row, second row will be added to the second row, similar. So this is the rules of broadcasting, right? So it won't throw any error, right? Similarly, if I have, let's say, m equal to something like np dot array, where you have column matrix, let's say 1, uh, 1, let's say 2, 3. Okay. Or say you have two columns 1, 3, 2, 5, 3, 6. So how your m will look like? M will be your this column. One, you have 3 rows, 2 columns. Now let's say you define b as np dot array, and now I have only one column, which is, let's say, 1, 2 and 3, right? Can I add m plus b? What will happen here? So it will be added column 5, right? So what's happening here? If you look at the shape of m dot shape and b dot shape, here the first dimension is same 3 cross 3, and the another dimension is not same, but one of the that value is 1, right? So it will stretch this matrix will stretch to bring into the same shape as the this one, right? So this will become 3 cross 2, and how it will do? It will create a new column. It will just replicate the very first column, right? And then it will be added, right? So you will have 1, 3, 2, 3. this column will be created, copied, and to create a new columns, and b will become 3 comma 2, and then the addition will happen, right? Similarly, you can do minus as well, right? And this you can think as like in k means you do find the distance of all the data points from a single point, and that single point you can think as a centroid, right? So here you find the difference from each of data point from a given vector, right? Given vector. So here you need not to create the copies every time. You just take data matrix minus the vector itself. That will do the task for you. Every data point will be subtracted, right? So such kind of operations you can do for NumPy. So NumPy allows you to do such operations. Okay. Okay, so this is what this broadcasting means. Now the next topic is the advanced indexing.
Sir?
So from yes,
So suppose we want to add a vector to all the columns then.
vector to a all the columns. That's what here happening here, right? So here you have if you look at the M here. So if you have M here, so M have 1 1 3 2 5 3 6, right? Now you want to add this 1 2 3 to all this to this vector. So 1 plus 1 2 plus 2 3 plus 3 will be here. 3 plus 1 5 plus 2 6 plus 3 will be done, right? So that's how it's taking place. This operation is taking place.
Sir, for a 3 by 3 matrix, then if we add a vector, then it will add it to the rows or columns.
No, if you are saying that if I have 3 by 3, right? And you have 3 comma 1. So it will first it will stretch to bring you to 3 comma 3. It means that you are creating new columns. So column wise addition will take place. Is it okay?
No, sir, if the number of rows and columns both are equal to 3, it is a square matrix.
Yeah, so
And
that's
we
what
add a
I'm saying.
vector.
Let's do that. Well, you have, let's say, three columns here, right? And here as well, let's say this one. Okay, so in this case, you have 3 cross 3, 3 comma 3, right? Now you are adding this vector. So how it will do? It will here it will become same shape as this one. So it will create two new columns, right? The same as the first column. Okay, and then the addition will take place. So you are doing column by addition, right? So m plus will
So
take place.
would it be allowed if, B is of 3 cross 2?
No, then it won't be allowed.
Okay.
The rules of broadcasting is that at least one dimension should be same, which is the same here, right? Three. The very first dimension is same. The another dimension, one of the values should be one. So another dimension is the columns where it is one here. If you pass it 2 here, then the addition will not take place.
Okay. Got it.
Okay.
Sir, if it is 1 comma 3, then it will add it to the rows.
Then it will be row same row will be added to each and every row of M.
Yes, sir. Here it is getting added to the columns.
Yeah, here it is added. One column is added to the every columns of M. Okay, so this is how the broadcasting takes place. Now let's move to the next part where you want to do indexing. Let's say this is your M, and I just take the copy of this, and I want to do the indexing. Indexing means what? You can just use the square vertex to indexing it. So if I pass the 0, if I pass 0 here, so it will create the very first dimension, which is your first row, 0th row, right? So 1 comma 3 comma 6. And again, if I pass, let's say I want to pass 2, so it will give me the second element from there. So 0th row and the second column. The value from the 0th row and the second column. Second column means the indexing you start from 0, right? So third column you need. So here this is your first row, and the third column is 6. So 6 will be taken out. Or what you can do, you can just pass 0 comma 2 as well, right? So it means that the element from the 0th row and the second column will be taken out, right? The 6, which is 6. But if I want to take different rows at the same time, let's say I want to take out the first row and the third row. So in this case, what you can do, you can pass the indexes of those rows as a list, right? Now I will pass those list indexes, zeroth list, and the second rows I want to take out. It will give me these two rows, the zeroth row and the second row, right? Similarly, the columns as well you can pass. Let's say I want to take out only the very first element from these two rows. I just pass those index. So that index means zero. I just want the very first element from these two rows. I mean, I just want 1 and 3, right? So it will be taken out as 1, 3, right? Or if I want to, let's say I want to take out as a second column element as well from these two rows. I can pass the indices of those, right? So that's how the indexing will be taken place.
So do we also use colon also here?
Yeah, slicing also you can do. Right, slicing means, let's say you want to pass, you can pass from 0 to 2. It means that you have the very first two elements, right? The last
First
one is not
rows.
counted. Okay. Similarly, let's say you just take the second element. It means that you will from first two rows, second element will be taken out. Okay, so that's how you can do the slicing as well.
Sir, is there any other notation also like you have written in line number 41 for slicing?
No, not any other, but these are the common that you can
No,
take.
like using slicing also, do we have like you have written in line number above this first one, 40, M0 in square bracket 0 and then 2. Do we have something like that over slicing type here also?
Slicing where you have not continuous rows, right?
Hmm.
No, then you have to pass the indices of each rows.
No,
Otherwise,
what I was,
slicing.
so what I was asking, like, can I write M,
Hmm.
then in square bracket 0 colon 2, and then again square bracket 2? Will that be valid? Close that, sir. Yeah,
And
and then
then
again
2.
2. Yeah.
No,
Okay.
it is not working. Index 2 is out of the bound with size 2. Because what's happening here, you have only these matrices, right? These two rows.
Hmm.
Now indexing will happen from this matrix,
Yeah.
right? So in this matrix, you can pass, let's say I want to take the first row, which I can pass as 0. Right? Now 1, 3, 2. So here it is creating a new array, right? So in this
Yes.
array, now you can do the indexing in this array.
Okay.
Okay. So to make sure that if you're finding from the original one, you just take rows and columns you can provide here.
Sir,
this
in
is
43, the two are identical in 43.
40.
41, cell number 41.
Here because M0 will create the same very first row, right? So if I create the M0, it will create me it will give me the very first row.
Yes.
Right.
And then
So here,
second,
yeah.
third
So
element.
these are two same in this case.
Same, no? Okay.
Yeah. So this is what advanced indexing means. It should go here, but I've done above. It's okay. Okay. So you can retrieve any elements by just giving the indices of that rows and columns. Okay. Now, in this case, let's say you have this M, whatever I've defined before. And now in this M, I just want to take out the elements which are positive. Right. So let's say there are some negative numbers as well. So there you can just make use of this M greater than 0. It will give me the Boolean values for all those elements where number is greater than 0 or positive, right? So it give me the Boolean values. Let's say true. It will give me the true values and the false values where the numbers are less than or equal to 0, right? So if I just take 0 here as well, it give me the false here. So this indexing you can do, and then you can even do this Boolean indexing to take out those elements, right? So I'm taking out those elements which are positive, right? So M greater than 0 make sure that it gives me the Boolean values, true or false values, whether whatever conditions we have provided, right? Now I can do the Boolean indexing. Boolean indexing means that it will take out only those elements where true is present, and it avoids those elements where the false is there, right? So this is the way you can apply the conditions to take out the elements, right? And why this is created in just an flattened array? Because number of rows, number of columns won't be same because you have created in here all three elements will be there. Here only two element will be there, right? So shape will not be compatible to form a array, right? A right shaped array. So in this case, what it will do, it will create a flattened array. Now you can change it into a desired one. Let's say I want to is safe into 2 comma whatever that is, right? So now it has created a matrices, right? So with the all the positive elements. So that's how you can use the Boolean indexing to apply any conditions, right?
We only want to find the index of these numbers, not the numbers themselves. Like when you actually put it as m greater than 0, it gave true false. If I want to know the positions or the indexes of the true and the false, how do we do that?
Sorry, I didn't get. You want to indexes where the positive present, right?
Correct. Only the indices, not.
Then you can just use m greater than 0, and let's say this m greater than 0 will give me the true and false, and you just take out those indices where true is present or false is present, right? So here there is function in NumPy which is your what is that function? Give me 1 minute, let me check. Not this one. Yeah, give me 1 minute. There is one function which directly gives you the indices to find out which values are present in the. Is this covered yesterday? Someone is saying that this has been covered.
True is covered, and finding the numbers is covered. I'm not able to recollect if.
No, this particular collab has been covered yesterday.
Yes, sir. Yes, sir. Tomorrow, yesterday was covered, sir.
Yes, sir. It was covered yesterday.
Oh,
Not
then
the whole
why?
collapse, sir. So some topics were missed.
Okay.
Sir,
Like
important
last
what covered, sir.
miscellaneous functions was not covered.
Oh, then you
I
must
think
have told me.
yesterday's session was more than 2 hours. So at the later part, it might have been covered.
Yeah,
not
yeah.
all of us were present.
Okay. But after that, I don't have access to those remaining collabs. I will move to the regression part. I was told that this collab was not covered, so that's why I'm doing this.
So you can go ahead with this only.
Yeah. Let me check that function. There is one np.where, but I'm not sure how it make use of the true values. Okay, I'll check that and let you know. Okay. So here you just use this one, and so now just move ahead of it. Yeah. So there's one question for you. You can try this out. You have been given a weight vector, you have been given a data matrix, and the corresponding the labels. Label means you have 4 examples and the corresponding label vector. Now you want to find the accuracy. Accuracy means that how to make the prediction. First, you make the prediction. Prediction means that W transpose X, right? So W transpose X will be, if greater than 0, it is positive. If less than 0, it's negative, right? So you will take the W transpose X and then check what are the predictions. So if the W transpose X is greater than 0, the prediction is +1, and it is less than less than 0, the prediction is -1, and check how many are correctly predicted. That would be your accuracy. So this is one question for you that you can try out. Check first, find the predictions for each and every data point here, and then compare with the true label. So this is your true labels here, right? So that you can try out, and you can apply only NumPy functions. Okay.
So day 1 collab files 4 and 6 is not covered. 1, 2, 3, 5 is covered yesterday.
Okay, which one are not covered?
4 and 6. No, 5, the 4.
Okay.
Sampling and visualization bar, histogram scatter.
Okay, so that we
Then
can cover tomorrow or day after tomorrow. We can continue from the regression that whatever we have covered till now, it is sufficient to go to the techniques.
okay.
Okay. Okay, so is this part covered? This next part where we do the functions like sum, variance, mean along the rows, along the columns. Is that part covered?
Yes, sir.
Yes, sir,
Okay.
but sir, left, right, and last miscellaneous functions were not covered.
Okay, so I'm skipping this part because it's already covered. So you can go to the video recording. And
The video
if not,
uploaded.
even previous terms workshop, you can go to those video part where it is covered completely. Anyway, it is covered yesterday, so I'm skipping this part.
Won't that be required for today's session, sir?
Not
Yes.
actually.
Okay.
Okay, so we can move to the regression part now. Let me share my screen again. Okay, so today, now let's move to the regression part here. Okay, so we'll do this NumPy library. We apply only NumPy library to get the. Okay, so okay, so all of you have must done the MLT course, and you must be familiar with all the convention that we have followed in the course, right? So in the course, we have followed the data matrix of the shape D cross N, where D are the number of features and N is the number of examples in the data set, right? So each column in the matrix is your one example. You have N such examples, and each row will denote your features, right? So element in the first row will be the first feature value, second row will be the second feature values, and dth row will be dth feature values for each of an example, right? So this is convention that we are going to follow here. And label vector is this is a column vector of the shape n cross n for so these are the associated label for all n examples, right? So by 1 to by n, this is the label to the first example, this is the label to the second example, and this is the label of the nth example. This is the convention that we are following, and we'll stick to that part, right? Now, so I've created a toy data set here, and you can look and you can even understand what's happening here. I just created some random values here, some random values between -1 to 1, and np.arrange will give me some equidistance values between -1, -1, -2 to 2, and with the step size of 0, 0, 0, step size of 0.01. So such some values will be created from -2 to 2, and I've reshaped into 1, -1. And I'm saying that in the training data set, take only one feature and decide how many data points are there, right? So you have only one feature. Okay. You can even create more than one feature. You can try out by yourself. And how your labels are associated, you can look at this formula here. You have some cubic relationship with the features, right? Because you have only one feature, and you can think as you can look at here. You have x cube plus 3x square plus 4, something like that, right? So you have some cubic relationship with the features with some noise, and noise means that every data points have some noise with that, right? So you have some curve of cubic curve, but the data points are associated with some noise, right? So this noise is coming from the normal distribution. Normal distribution with the mean 0 and the standard deviation of 1 or variance 1. And I've reshaped into the because every data points are coming with the noise. I'm saying that how many numbers to be generated from the normal distribution? These many numbers, right? Because the columns are the number of examples there, right? So these many noise has been generated, and I have added all these noises to each and every data points, right?
Excuse me, sir.
Hmm.
For a real data set, we don't need to do that, no? We don't need to add the
For
noise.
real data set, you just make sure that the shape and are compatible for your model. How you are gonna use them, right? So it's just a toy data set, right? So if I
What
look
is
at
the
X,
seed?
huh?
So what is the seed
Seed value means
in the
it controls the randomness of the whatever you've created, random numbers you've created. It means that every time you run this code, you will get the same randomly generated numbers.
Sir, why do we need to reshape the y? Because it's already x is already shaped, right? We are just changing the deriving the value, right?
This one,
Yeah.
because here x train dot shape was so if I do this thing x train dot shape, it was 1 comma 400, right? So 1 comma 400. Now you have to bring byte train into 400 comma 1, right? That's why I have to reshape it. So if I look at this shape now, byte train dot byte train dot shape. So you have 400 examples, and for 400 examples, these many labels are there, right? And you have only one feature in a data set with 400 examples.
No, my question is that reshape, we can directly transpose it, right? Without in the y, without reshape 1 comma minus 1.
Here, this one.
Yeah, yeah.
You
If you
can check
remove
this
that,
out. You
okay,
can
okay.
check this out, right?
Oh, okay, okay,
It's
sure.
called, right.
Excuse me, sir.
Yeah.
Sir, what is this RNG thing here? RNG dot normal, and could you please explain this whole piece of code after this
So
plus sign?
this is the module. This np dot random default RNG is a module. RNG
Okay.
stands for random number generator. So it
Okay.
means that you can generate random number from given distribution. You can generate from the normal distribution some integers from a given range. Such kind of functions are present in that module. So that there are
Yes.
many functions in that modules that you can make use of to generate the random numbers. Like you can generate numbers from uniform distribution, from normal distribution. Like let's say RNG I'm calling here. This model I'm calling as RNG. Now I want to
Yeah.
convert. I want to convert I want to generate number from the normal distribution. So I can use the function rng.normal. It will give me the randomly generated number from the normal distribution, and I can pass the parameters of the distribution, which is 0 and 1, which is the mean and the variance, right?
Yeah. Okay, sir. And so, how it is reshaping into four cross one thing, the wide range shape.
4 comma.
Yeah, 400. Sorry, 400 cross one. How it's reshaping this y value?
Okay, this reshaping is only for this random generated number. Remember, because randomly if I do rng dot normal, so this rng dot normal and with the shape 0 comma 1, it will give me just a single number, right? It's just a single number from this distribution. Now I want for every data point I want to add some noise, right? So I'm saying that generate these many numbers. How many? How many examples are there in the data set? Generate these many numbers
Yeah.
and add each numbers to your label, right? So now if I check the shape of this, if I check the shape of this, it's 400 comma 1, right? But I want to, but here if you look at this shape, this is your 1 comma something, 1 comma 400. So to make this additions happen, I just reshape into 1 comma 400, right?
Yeah, yeah.
Such that this addition takes place.
Yeah, okay. But sir, then the answer should be this some point should the white range, the answer should be in 1 comma 400 only. Why it's with the inverse thing 400 comma
Then
1.
I transpose this. Then I
Okay,
have
okay,
transposed it.
okay. Okay, sir. Okay, sir. Got it. Thank you.
So can you explain the signature of this normal function?
Sorry.
Signature, sir. Yesterday, sir, I taught like np.normal, and then we give a question mark. We get the signature of this using help text.
Okay, this
To understand.
this mean, right?
Yes, sir. Using that.
You can here you have a generator here, so you can make use of different functions like RNG generator, RNG standard normal or whatever. So you can use RNG dot normal. Here you can pass the slope means the mean, and scale means the standard deviation, and size how many numbers you want to create, right? So it will give me the number of a number from the normal distribution with the given mean and the variance.
So
Sir,
what
we
is
can
the third parameter that we are passing to this normal function? Extreme dot shape, what does that mean?
That is size. How many numbers you want to generate from that given distribution?
Okay. Okay.
Sir, we set the seed for the range. We set the seed for 101. That is for every time we run, we should get the same value, right? We
Same
setting
value,
the seed.
yeah.
Then in that case, for the normal also, we should set the seed, right? Otherwise, white train will be varying value every time.
In the module itself, I've set the seed. Then I'm using the same module to generate the number. So I need not to do the again. I need not to set the seed.
Okay.
Okay. So now you can plot this as well. I can make you the plot library. I can just use the scatter plot.
Sir, I have one question.
Hmm?
Sir, what is the difference between arrange and linspace?
Linspace and arrange. Okay. So let's check that. np dot arrange. If I just pass in numbers to that, let's say 10, so it will give me a number, equidistance number from 0 to 10, right? And linspace np dot linspace, I think is only from 0 to 1. Let's say I pass 10 here. Right, it should not work.
Linspace actually does
Sir,
is like
could I explain,
partition
sir?
a line into number of points we want. And
So we have to mention the start.
Sir, linspace basically create the division between the 2 points. And if default value is 50, if we take the point 0 to 1, then default it divided 0 to 1 into 50 pieces. And arrange does not do this type. So
Arrange also will give you the equidistance numbers, but linspace you can provide the starting value, stopping values, and specified
then arrange
intervals.
function we can like give the starting value, ending value, and it will just generate the numbers. Linspace is basically dividing a set of into points, I guess.
And even in arrange, you can pass the what distance you want to specify for two numbers, right?
yes, sir,
Right?
yes, sir.
So in linspace, you can pass how many numbers you want, and in the arrange, you can pass what step size you want to use to generate the numbers.
I think the only difference is that in linear space we get decimal points. In a range we can't get decimal numbers.
Yeah. No, linear space also you can get the decimal numbers, not an issue.
Yeah, that's what I'm saying. In a range you can't get them. Only in linspace you can get decimal numbers.
You can get decimals in a range as well. Just need to
Yeah, in
provide.
the both you can get the decimal numbers, not an issue. Even in our data set, you have got the decimal values. I've used the arrange function only, right?
Sir, in the documentation, they have said that when using non-integer step, it is better to use linspace.
Yes, okay, but you can make use of both the functions, not an issue.
Yeah, because the step argument is there in a range also.
Sir,
Right, so
Sir, a range doesn't partition something, right? Linspace partition it.
yeah, in the
A
equidistance,
range
even
generates that much number from the given, like suppose
Yeah,
if I
correct.
give 1 to
Yeah,
100,
so arrange,
let's say only 10 generate 10 numbers, so it will be generating 10 numbers.
yeah, in the given range,
Yeah.
right?
Sir,
Can we create the scatter plot between multiple features and a label?
It won't be if you have multiple features, because multiple features you cannot create the two higher dimensions plot here. here I can easily do because you have only one dimension feature. So features versus labels, right? That I can do here. So if you have multi-dimensional data set, then plotting won't be easy because you cannot visualize higher than 3 dimensions plot. Or scatter is just one versus one, right? So scatter plot cannot be drawn for more than 2 dimension data set. Right, so here I'm just plotting x versus y, right? So this is your first features against your label vector, right? So this is how your data set is distributed. And in the similar manner, I have created the test data set as well. And the same way I've created, but some lesser numbers, right? So uh, yeah, that's how I've created a toy data set. If you are not getting this part, you can avoid this because it's just a data set generation part. The actual part is to create a linear regression model. Okay, so let's study about linear regression model, and I'm pretty sure that all of you know these things. So a linear regression model is that we are assuming that all the features have linear relationship with the labels, right? So I mean the relationship between the labels and the features are the linear ones. So all the features are related with some linear function in the linear subspace, right? So you have this W1 up to WD, which are your weights that you need to find out. And this linear relationship you can write as X transpose W. So X transpose W means that for any data points you just do X transpose W, you will get the predictions once you have the W vector with you. So our task is to find this W, and how to find this W. And this particular formulation says that uh, this plane or hyperplane, whatever is this, if it is in d-dimensional plane, so in d+1 dimension, it is a hyperplane which passes through the origin, right? And we want our hyperplane to have some intercept on the label vector as well. In this case, I don't want to pass the origin always. I may have some distribution here as well, and in this case, I want to have some intercept on the by label vector as well, right? So in this case, what I will do, I just add the constant as well, right? This constant I'm calling as a W0, and to make consistent, I just add a dummy feature which takes value 1. So I make sure that my hyperplane that I'm learning or I'm training doesn't pass to the origin always. It has some intercept on the label vector as well. So I'm calling X0 as a dummy feature with some constant W0. Now my weights are D+1 weight. So I'm to learn D+1 weights, right? So my weight matrix or weight vector will become of the shape D+1 comma 1, and X is again D+1 because I've added one more feature which is dummy features taking all values as 1. So my X is of the shape D+1 comma n, right? So I can add one row, very first row as my dummy feature, right? Or even if you add into the last, your last one will be last weight that is learned using model will be your weight. If you are adding the very first row, your first W in the weight matrix will be your constant one that you're learning. Right? So this is the model that we are learning. This is for this is the predictions here for one example. So how to add the dummy features? For that you can make use of the row stack and column stack and the so let's first generate the dummy feature. Dummy features will be np dot ones, and how many ones I want? How many ones? The number of examples, right? For every example, I will add a feature, right? So this will be your x dot shape, and with number of examples are columns. So this will create a ones, and I can make use of the. So
Sir, what is the meaning of one in x train dot shape one?
The number of columns, right? X dot shape is a tuple. So number of columns I want, right?
Okay, sir.
X train, I'm calling it X train now, and or just call X here and X train, and I can make use of np dot row stack, and I can pass the tuples. I want to add dummy feature with the X train, right? So if I look at the X now, you have this X, which is your if you just check the shape here, you have two features now, and 400 examples. The very first feature is your the column, right? So if I take just the very first row here, it will be all ones because this is your dummy features, and now you have two features. One is a dummy feature, another that is already given to you. Now you have added your dummy features. Similarly, I can add into the trash data set as well. I'm calling it X test, and you can use np.row stack, and I can pass the dummy features I have to create because number of examples are different there. So I np.ones, and how many I want X test dot save and one, and then I can add into the X test. Right, so this is the dummy feature addition in both X shape and X test. I can check the shape of X test as well. So in the test data set, you have 200 examples. In the training data set, you have the 400 examples, right? Now, once you have the model, your task is to find this W, right? For that, you define a loss, and loss we define as a sum of a scared error, of what? You have the actual labels and the predicted labels, and you add, you find the square of that, and for each and every examples, you find the sum of that, right? So this is your
Excuse me,
loss.
sir. Sir, how it came 200 instead of 400 in the above part?
No, in the test data set, there were only 200 examples.
Okay.
In the training data set, there were 400 examples, and in the test data set, there are 400 examples, right? So you
Okay,
have
sir.
400 examples in the training data set. In the test data set, you have 200 examples.
Okay, sir.
Okay. Right. So this is your loss function. If you are writing the matrix form, it will be x transpose w minus y transpose x transpose w minus pi. And you have already seen this. Now, how to find this w? You want to minimize this loss. For minimization, you have optimization techniques. One is just take the derivative with respect to w and set it equal to 0. If you take the derivative of this with respect to w, you will get x transpose w minus xy. And if you set equal to 0, W will be X transpose inverse. And this is pseudo inverse here. You just take inverse X into y, right? So this is the W that you get using your normal method, right? So for that, you can just simply define a function. You can call it weights. Right? And what I need, I have access to the data set and the label vector. And I just can simply return np dot. So for inverse part, there is module in the NumPy which is linelse. So this linelse, what it does, it has many linear algebraic functionality like finding inverse, finding norm, or finding the solution of given equations, finding transpose, or many finding eigenvalues, eigenvectors. All those functionality are present in this module np.linelse. And for finding pseudo inverse, we have function p inverse, right? So this model you can make use of to find the use the functions of the linear algebras, right? So what I want to do, I want to do x transpose inverse, right? So x transpose I can do as x into x transpose, and then I can do x into y, right? So again x into y, right? So this will be your weights. What happened? This. Right. So if I find the weights in our case, you have X data set and byte train, right? So you have only two weights. This is your constant one, W0. This is your W1, right? So these weights you are getting. Now, how to make the prediction? So you can define the function predicts, and for predicts you need X and the weight vector, and the what is the prediction? Prediction is just X transpose W, right? So this is your prediction X transpose W for every example, because X is of the shape D cross N. X transpose will be N cross D. This is D cross 1. So X transpose W will be N cross 1. It means that each and every element in X transpose W will be prediction for your each and every data point, because the prediction is your X transpose W, right? So if you do X transpose W here, each element here will be prediction for each of for all n examples, right? So you can just simply return here just simply return X transpose W. Right? So in our case, you can find the prediction. So what will be the prediction in this case? You can make use of this function predict, and I can call this as, let's call this W, so that I can make use of this here. And your data set is your X, and W will be right. Now this is your prediction here. So these are the predictions for all those 400 examples, right? So you can plot the weight vectors as well. And for plotting, what you can use. So have you done this matplotlib library yesterday?
Yes, sir.
Yeah, just not all the types of chart, just started.
Yeah, so that we make use of only. So first, let's just first draw the scatter plot of the training data set only, X train, right? X train and by train. Right. Now, if I want to just add the learned weight vectors as well, then in this case, what we can do, you first get the axis, I mean the dimension of this axis, x-axis and y-axis. For that, you have function GCA. GCA says that you just get the current axis. GCA means it is stand for get current axis. So whatever you have used dimension for this plot axis, it gives me those dimensions, right? So I can call it axis, and from here I can find the limits of all those things, right? So let's say I want to x values. X values means the dimensions. What are the minimum values, and so I can use first I can just simply let's say where is that? Yeah, so here I can just simply let me do that. If I do axis dot get x limit, what it will do, it will give me the limits for x-axis, right? So x-axis is starting from -2 to 2. Here it is starting from -2 to 2. So it give me the limits of those x-axis, and what I can do, I can just simply use these data points np dot array to my x values, right? And I'm calling as x values, and similarly by values is what. So what I'm doing is I'm just finding a equation of line, right? The equation of line you can find using your just using your one data points, the x values, right? So you can use your model is W0 plus W1 X1, right? So you have model has W0. W0 is your W 0 plus W1, and you can multiply with the x values, right? Now you can plot these values, and you can simply plt dot plot. You can plot x values and y values against the y values. So this you must have seen.
I didn't understand y values, how you calculate it.
So this is your let's say this is your endpoint, right? This is -2. For -2, what will be your prediction? Just pass into x W0 plus W1 x, right? This is your model. How you make the prediction? You just pass in the model. Model is your W0 plus W1 x. Right, so that's what I'm doing here. So first value is -2. I'm pass here, I will get the corresponding y value. Similarly, the next limit is your, let's say, 2. So what will be the prediction for 2? Just pass into the model W0 plus W1 x, right? Now you have two data points, this one and this one, and just create the line. That's what I'm doing here. And you can make some different color as well. Let's say I want to use line with the red color, right? Or red colors with the line, right? So this is your model. This is your trained model here. right? Now you have predictions, you have the weight vector, you have to evaluate your model, how well it's performing. For that you define RMSE loss. RMSE function, which is root mean squared error, is just the prediction values. This is the actual values minus prediction values, square for all those examples and take the mean of that, right? And take the square root of that, right? So you can define the function for that as well. You can define loss, and loss you can make use of the true labels, and you can just take by the two labels and by head to be let's call those the predicted labels, right? And just simply return what I can return. If you look at this is the square root of the mean of this quantities, right? So what I can do, I can just take by minus by head, and take the square root of that. That is your 2, and just take the mean of that, right? Because this is the mean of these quantities. I just take np dot mean of these quantities, and then just take the square root of that, right? So you can do np dot sqrt, right? So it will be your loss. So loss will be your in this case you have true labels as byte range, and prediction label is your make use of the fit function for x into w, right? So this much loss you are having for your the length weight vector length models. Okay. Now this is the one way to find the weight vector, where you just take the derivative, set it equal to 0 and get the weight vector. Now another way is the optimization. Another optimization based using use the gradient based methods. Gradient based method says that you start with some weight vector and then move into the directions of the negative gradient, right? And it makes sure that you always go into the local minima, right? Or global minimum in the case of convex function. So linear regression model is your convex surface loss. I mean this loss function that we have defined is the convex surface. So in this case, it will converges into the weight vector, right? So the update rule in the gradient descent is that in the kth iteration, if your weight vector is wk, you just go into the negative direction of that negative direction of the gradient. You find the loss function a gradient of the loss function at that point, and then go into the negative direction of that gradient, right? And with some step size. This is step size or learning rate. We call it alpha. And so your weight update rule is wk minus alpha with this gradient, and this gradient we have already set, right? So you can make use of this gradient descent as well. So I can define function first. Let's say define gradient required at your data matrix and the weight vector and the label vector as well, right? So here you just return this particular expression, which is your xx transpose w. So x into x transpose into w weight vector minus x into pi, right? X into pi. So this will be the gradient at a given w, right? For the given data matrix, the given loss function, right? Or loss function, the squared error loss function. Now I'm to use the gradient descent method. So for that, I'm defining a function. The function, let's call this gradient descent. And for gradient descent, what I need data matrix and the label vector, right? And in this case, I can start with the random weight vector. I'm starting with the zero weight vector. So I'm calling it W0 to be np dot zeros. How many zeros I want? How many weights will be there?
X dot shape of 1.
Shape of?
So for the grade, so for the gradient, do we need the dummy feature?
So here the parameter that I will pass will be dummy features 1.
Yeah, but right? Do we require dummy feature for the gradient descent?
Yeah, of course we require. Right? That's how we design your model, right? Your model should pass through should not pass through origin always. That's how you define your model. Once you define model, then you go to the loss function. And this is your optimization technique, different optimization technique. When we use this derivative and set equal to 0, this is another way of optimization your loss function.
Okay.
Okay. So np dot how many the number of features equal to, right? So number of features are the first dimension of that tuple, right? So these many zeros I require, and let's say you have iteration as well. So you required with this you also required your learning rate and number of iteration as well. So learning rate I'm calling at eta, and the number of iter I'm calling as n iter. Okay, and then I can use for I in range n iter. Every time I do I just update my weight vector equal to I just update W0 equal to W0 minus eta times your gradient, right? So I can make use of that function gradient here. Gradient requires parameter your label, your current position of the weight, and your label vector, right, which is your phi. Okay, and for every iteration I do that and just return the last one, the updated one, right? W0. So this is how your gradient descent works. So in this case, if I do for our given data set, I can use grade descent and for x train or x itself, and by train, let's say learning rate to be 0.01 with let's say how many iterations I want. Let's say 10 iterations I want, and in this case I will get 4 weights. It should be 2, right? What is the shape of W here? W0 dot shape. It's a 2 comma, I need equal to 2 comma 1, so I can reshape it. Shape into 2 comma minus, right? Then 2 comma 1, and if I do this now, yeah, now you now you have 4 weights, no, 2 weights only, right? This is minus 308551 and this one, right? Initially was also only 2 y. Okay, anyway, so you have these weights, and you can look at the difference here. Initially, the weights that you have learned from the normal method, you got the weight as, what was your weights there in this case? You have let's draw that W equal to 7 and 4. Here you have minus 30 and very far. So what may go wrong? You can increase the number of iterations. Let's say I increase the number of iteration. In this case, what will happen? It's coming closer, right? On increasing number of weights, or even if I go up on there, it's going down. It's going above it's going to infinity. It means that your learning rate is too high. It's taking jump, very high jumps, right? It's just oscillating around that. In this case, now it becomes very close to that. But once I decrease down the learning rate, my weights vector is going, we are going slowly to the local minima, global minima, right? So here you can make use of the lesser iterations, right? So that's how you can play around with different learning rates with different iterations and see how your optimization techniques behave. So when I set it to the low learning rate, it's happening that it's taking jump around the local minima, and taking jump means that even going down very far away from your minima and going to the infinity values, right? So jump are very high, steps are very high. So it decreases my learning rate.
So this is the way how we should do, because now every changes you make, there's a huge difference in the result, right?
Yeah,
so
correct.
So how do we know that it is actually what do you call the correct value? Because now we know that what is the correct value in the earlier method. That's why we are trying to reach that value.
No, that for that you define the loss, right? You have idea of the labels, and then you define the loss functions. And if your loss coming high, it means that you are not closer to your minima. You want to loss to decrease down. You can plot your number of iterations versus loss number of, or say you can plot learning rate versus loss, something like that. You can plot, and you want to choose that value where your loss is minimum, right?
Okay.
I'm not just
Can
comparing the weight vectors.
okay, can these two be a hyperparameter? And is there any way we
Yeah,
can?
these are hyperparameters. These are actually hyperparameters. Learning rate and your number of iterations are hyperparameters. So you want
Okay.
to choose best. Best means where your loss is minimum.
Okay. So is there any other method to like to find the best hyperparameter?
No, for hyperparameter, you have only search methods, hyperparameter tuning methods, where you try different candidates for those parameters and see for which parameters, for which values of those hyperparameter your loss is minimum.
Okay.
And also, instead of a for loop, we can use a while loop and make it converge until the loss is less than a certain value, right?
Yeah, that also you can do. If you want to that way, yeah, that also you can do.
Okay, sir.
So in this case, if I want to find the predictions, I can make use of the function prediction. For prediction, you need x and the weight, which is your w grade, and this will be a prediction, right? And you can find the loss as well, how many loss suffer. For loss, you have x, you have w grade, and what? No, for loss you have by train and the prediction, right? So you can use prediction x over w grade. Right, so here in this case the loss is higher, right? So initially it was 4 point something. Now you are not close to that minima, so loss is higher. So even you can go to higher iterations as well, right? So in this case, let's say I'm going to higher iterations, I mean large number of iterations, and your loss is decreasing down.
Excuse me, sir.
Yes.
Earlier, when we were using this one linear algebra class, so in that case, what is the underlying optimizer?
This one,
yeah, the first
here
one.
Here you are using this normal method where you said you have this optimization. You have to minimize this. This is a square function, right? So just take the derivative with respect to w and set equal to 0. This is the first derivative test for finding the optima, right? Or minima. Right? Normal method that we call it. Now this is the gradient based methods.
Yes.
Okay. So this is your gradient descent. You can plot the number of iterations and loss. How you can do? You just keep the track of iterations and the loss. Let's say your number of iterations are these many. You want to take 10 iterations, 20 or say 50 iterations or 100 iterations or let's say 1000 iterations, and every time for every iterations you just track of loss values. So you can define a list, loss, and a empty list, and every time you just append the loss function, right? So let's say for I in an iter, I just find the weight vector. So w, let's say w equal to your grade descent with your x and gradient descent with x and what by train, right? By train, and fix any learning rate. Let's say 0.001.
Here,
or say
alpha
0.
is the learning rate. Is that correct?
Alpha is the learning rate.
Okay.
Or eta, I'm calling it here, right? Eta or eta. Eta I'm calling here. That is your learning rate.
Okay.
And here with the different learning, with the different iterations. In every W, you can just find the loss. So I'm calling it LS and just make use of the function loss and loss required by train and your prediction. So prediction over. So or even you can use prediction here. Let's call this prediction to be prediction using your X and W, right? And you can find prediction and just append your loss function here, right? What happened? List is not callable. Okay, so here I'm calling it loss. So that is just, it didn't get here. So this loss you have to define, right? Okay, now you can plot this thing. So you can just simply use plt dot plot. You have a number of iteration on an x axis, and on the y axis you have loss, right? So you can see that when the iterations were uh, iterations were 10, right? So when iteration were 10, your loss was very, very high. And when it goes to 50, it goes some closer to 4.5. And remember, 4.5 is the minimum loss, right? So it is now decreasing very, very less. So number of iterations, even you can keep to very low. And you can even do for this plotting for plot number of iterations versus you can plot number of you can plot eta versus loss, right? In this case, you can find. So here, rather than iterations, you can vary your learning rate and set a particular eta or learning rate, right? Then that you can plot. Okay. So next thing is SGD. So what is the difference between SGD and gradient descent? What is how you define SGD? Stochastic gradient descent.
Only take a part of the training data.
Right, because this becomes computationally very lengthy, because if your high number of there are many examples in the data set, this x transpose w, this expression x transpose w minus x has become very computationally lengthy. So what we do, we don't make use of each and every examples to find the gradient. We just make use of in the batches or single examples, right, to relax the to make it less or sufficient for the computational part, right? So for that batches, we divide data set into different batches, and then for different batches, we find the gradient and then move into that directions, right? So this is not true gradient, but it makes sure that you, on an average, you are moving into the right direction, right? And on an average, not every time you are moving into the right direction, but on an average, it makes sure that you are moving into the right direction, right? So SGD part I'm leaving on you. I provided the code in the collab that I've uploaded in the folder. You can go and check how I've done this. But this is your good practice for you. You can try out. I just give the hint. First, divide your data set into different batches, and for different batches, you find the gradient and do the update, right? So it's just the applying your loop, and inside a loop, you just define your batch size, and for that batch, you find the update your weight vector, and just start and loop. That's it. You need to do, and that will be a right practice for you. You just go and check how to do that. If not, you can go back to the collab and check the solution there, right? Okay. So this is your gradient linear regression model that we have learned, but we know that the loss is in this case loss is minimum because you have just values between 0 to 1, something like that, minus 2 to 2, something like that. So loss is not high, but we know that the original relationship is not linear one; it's a cubic one. So we are now moving to the kernel regression model. So what is kernel regression model?
Expanding data to higher dimensions.
Yeah. So it says that if the relationship between the features and the label is not linear in the d-dimensional space, what it does, it sends your data points into the higher dimension and make the assumption that in the higher dimensions your data set lie in a linear subspace. Once it comes in the linear subspace in that higher dimensions, you can apply a linear regression model into higher dimensions, right? So in the small d dimensions, if your data set is not linearly related to the or label are not linearly related to the features, then it sends into the higher dimension D, and it assumes that in the higher dimensions, your data sets lies in the linear subspace. There it applies the linear regression model, and that we have already covered all those part in the course, MLT course, and where we do some manipulations, linear algebra, and see that your weight vector actually nothing but linear combination of the data points, right? So your data points now in the higher dimension is phi of x, right? So this is mapping which sends your data points into higher dimension. So every data point become your phi x now. So your data point, if your original data points are x1, x2, up to xn, your in higher dimension, your data points are 5x1, 5x2, up to 5xn, right? So these are your data points in the higher dimension, and we have seen that your weight vector actually a linear combination of your weight data points, right? So this we have already seen. Now our task is to find this alpha, this coefficient, right? So and again we do some manipulations here, and alpha is comes out to be k inverse pi, where k is your this matrix k x1 this is your kernel function. So we don't do this, we don't find this phi explicitly. What we do, we just define a kernel function, and kernel function says that it's uh, here yeah, kernel function is just a function in a d-dimensional space where it takes two inputs values, and the output of this is the same as dot product into the higher dimensional space. Dot product of that transform data points into higher dimensional space, right? So if the kernel has taken input as x1, x2, so this kernel function value is similar to the dot product of phi x1 and phi x2, right? So this is the kernel, and every valid phi you have a kernel function, right? So for that kernel function, you define this kernel matrix, and your alpha comes out to be k inverse pi. This all theory we have covered into week 5 of MLT. You can go and check it out how it comes out, right? So I'm just briefly describing what we need. Here we have to find alpha. Alpha comes out to be k inverse pi, and for different valid mapping, you have a different kernel function, right? For what is kernel for polynomial? What is a polynomial kernel?
X transpose x plus 1 the whole power p.
Yeah, so this for any two inputs x1, x2, the polynomial kernel is defined as x1 transpose x2 plus 1 raised to power p, right? So now we are going to apply polynomial kernel in this case, right? So let's find this polynomial kernel. So first we are defining this kernel matrix, this k. So k is what? You just take the kernel function. So first let me define this kernel function x1 transpose x2 plus 1 raised to power p, and then define the matrix. I'm calling it this define poly kernel. And it takes your x and power, which power, polynomial power you want to use, right? And it just take x transpose x. So what will be x transpose x? Isn't it this matrix? This where it is there? It's just what will the this matrix x transpose x? What will be the ijth element of x transpose x matrix?
Covariance.
So x is your d cross d cross n matrix, right?
Yeah, so it will be D cross D matrix.
So this is the dot product of ijth element will be the dot product of ith data point and jth data point, right? Because this is the
Pairwise dot product.
pairwise dot product. So ijth element will be the dot product of ith element and jth element of the matrix, right? I mean ith row and jth column. If I look at the ijth element of x transpose x, it is the ith row of x transpose and jth column of x, right? So this is ith row is what? Ith row of x transpose is ith data points, and jth column of x is what? Jth data points, right? So this is the dot product of ith data point and jth data points, and that's how you define your kernel function. You take the ith dot product of ith and jth data point plus 1 raised to power p. You can do, and that will give you the all the element will be added to 1, and all the element will be raised to power p. So it will be a matrix of the shape n cross n, right? So this will give me this matrix, right? Because this is how you define your kernel function, right? Where ijth element is xi transpose xj plus 1 raised to power p, that you can get from here, right? This is small, right? How to make the prediction you make using this k. Let's say your test data point is xt. you find k kernel function for each and every data point from the training data set for that given test data point, and take the alpha I. So this gives the similarities with the every data points, and this gives the how much weightage to give to that data point, right? So and sum over all the data points, right? So this is how you make the prediction. Let's say you have m data points in the test data set and you want to make the prediction. So how to make the predictions? First, you have to find the alpha value as well, right? This alpha i's. So alpha i's is k inverse pi. So you can just simply define a function, define coefficients. I'm calling it, and for that you define x training data set, and you define the y as well, and the power of p, which polynomial power you want to use, right? And you just simply return k inverse pi, right? So k is k you can define from here. So I'm calling it k here, and I can call this function here poly kernel with x train and with power p, and here I can simply return k inverse pi, right? So inverse will be np dot lin alz dot p inverse, and this will be your k inverse. This is k inverse and dot pi, right? So this will give me the alpha values, right? So in our case, if I want to find the coefficient, this will be your x train, y train. Let's say I want to use cubic polynomial kernel. So you will get these many alpha values, right? Okay, what will be the shape of that? What do you think? What will be the shape? It's a n cross 1, right? So 400 cross 1, right? So this is coming correct. Okay. So how to make the prediction for the test data set? This is your training data set where you have n examples. Let's say in the test data set you have m examples, right? So how to make the prediction? You just take for any data points, right? Let's say you take only first data point xm, this xt1, right? So you find the k value, kernel function value with all the data points. This is just your, if you look at xtrain x test here, this xtrain transpose x test, so element will be something like that, where this is your first row of xtrain, first row of x transpose, right? So which is your x1 transpose and xt1, right? So this times I mean the dot product x1 times xt. So this will be your x1 times this one, x1 times this one. And for first data point, you just take all those elements times alpha, and that will be your prediction, right? Similarly, you can do for x2t, and so prediction will be easy. In this case, you can define prediction. It takes the training data set, test data set for which you want to make the prediction, and the power which polynomial degree you are using, right? X train, X test, and even you need pi for finding the k values, right? Or alpha values and power. So here you can just simply define this function, which will be your, first you find the coefficient, which is your alpha. I'm calling it alpha equal to coefficient. Coefficient will be your that function which required x train. What else it required? X train and by train, right? By train and the power p. Once you have alpha, you can simply use this function x train dot x test transpose into alpha, right? So you just simply return, or first I have to define k, right? K as well, right? So this will be your k. K will be your x train dot t. I mean, I'm defining this x train dot x test, and this will be your x test, and plus 1, the function kernel function value, right? Plus 1 raised to power p, right? Once you have this for every data points, now you can just simply use k transpose dot with alpha values a. Right, so you can make prediction for your x train Xtrain. I want to train the model on training data set. Find the prediction on the training data set as well. So you can use Xtrain by train and P, let's say 3, right? So it will be prediction. What happened? Case not defined. This case not defined.
So why are we multiplying Xtrain and Xtest?
This one?
Like the dot product.
This one? This thing you are asking?
Yes, sir. Yeah.
So here look how to make the predictions for any test data points, right? So let's say you have xt as your test data point. So how to make the prediction for xt? This is the formula. You use the kxi xt for each I and multiply by alpha I and take the sum of these, right? So what is kxi xt? Kxi xt will be this function xi transpose xt plus 1 raised to power p, right? For every training data point you do. If you have m data points for the test data set, what I'm doing, I'm just doing x transpose x train transpose xt. If this matrix look like this, for the first data points, I just take this element plus 1 raised to power p. That will give me the kernel function value with x1 and xt1, right? And I just multiply it with alpha 1. Similarly, I do for x2t, x2, the second data point from the training data set with the same test data set, right? Plus 1 raised to power p, and then multiply by alpha 2, right? So all these I do for first column. That will be the prediction for my first test data point. Similarly, I do for this second row. That will be my prediction for the second data point, right? Similarly, so I've just done that thing here.
So that means we can't get rid of the training data even for the prediction.
What gone wrong here? Yeah. So because training data set is required for your training the model, you can get rid of, but you have to define. You can define your own functions, and then you can get rid of these things. Okay, you can go step by step. In that case, you can get rid of this, right? So this is your predictions, and I'm calling this, let's say, by head. And if I find the loss now, loss will be your.
So that should be Xtest.
Sorry.
So the parameter of prediction. You have written Xtrain twice.
This is for modeling, and this is for where I want to make prediction. Right. So if I want to make prediction for Xtest, I can use Xtest, and then I have to use Xtrain and Xtest. Here by head and Xtrain Xtest. Gone wrong here.
K ultimately is a d by d, right? K ultimately is it d by d or n by n?
N by n.
Then should I ensure that the train and the test
So
sizes
that
are
case
the same?
different. That case different. Here it's not kernel matrices. It will be your n cross n. This will be your n cross n.
But the number of data in the training and tests are different, right?
Yeah, that is different. So this K will be your n cross n.
Oh,
it's not n cross n. This is n cross n. What is going wrong here?
That is a kernel matrix.
I think your definition of XT is not there. I'm not sure if XT, X underscore T is defined.
I think it should be only X train. Because X contains the dummy variable as well.
This is X test. Sorry.
It should need to be test, not T.
Yeah. Now you can use this to find the loss, which is 2.11, right? So 3 degree is doing better task, right? Even for the test training data set, the loss is coming to be something like 1 point something. So here you can find that loss on the training data set, which is coming out to be very close to 1 point something. And for the normal methods, I mean, linear regression model, it is coming out to be 4 point something, right? So here it is coming out to be 1, so it's working better, and we know that as well by the generation of the data set. Now you can plot degree versus loss. So same way you can do different degrees. Let's say degrees are your uh, 2 degree, 3 degree, 4 degree, 5 degree, or even say 1 degree, something like that, right? And you can keep track of every loss. So not calling this loss now, some different variable name. And for I in, or say D in degrees, I just find the polynomial. I mean, I can make use of all those functions. So first is your prediction. So prediction require, I'm calling this prediction will be your prediction on the X train by train, and let's say degree T. Every time I make a loss, I'm calling it LS to be loss. Loss is your by train and prediction, and then just simply append in the loss, right? Once I have this, I can draw my PLT dot plot. On the x-axis I have degrees, on the y-axis I have loss, right? Yeah. So you can look at for the 2 degree loss is more than 2, for 3 degrees it is coming, and even after that it is kind of same, right? So 3 degrees coming doing better task for our model part, right? So you can even find the loss for the test data set as well, and check how this loss function varies versus degree.
So how do we plot that the fitted curve?
Fitted curve?
Yeah, now like we have drawn the red line here.
In this case, you don't have access to the W, right? In the kernel regression, you don't have access to the weight vectors. That's how you, because W is defined for defining W, you need phi, right? This phi.
Yeah.
And we explicitly don't define phi. That's why we take a, seek that method, kernel methods. Kernel method just says that it doesn't need to define your phi explicitly. And if you have this access to this phi, then you can define W. And once you have W, then you can draw your weight vector. Weight vector, but here it is in higher dimension because weights become your, because you have thrown your data set into higher dimensions, right? Because initially it was 1 dimension, and you have thrown your data set into a higher dimension. So you have more number of features. So even their visualization will not be easy because you have your model will be your hyper surface into a higher dimension. That visualization is not easy. But anyway, if you here you need phi to find W, which you don't have access to this phi.
Okay. Or else can we take the X value with the lineage and take the X values and try to predict for each, and then is it possible to plot?
That approximations method, like
yeah,
that method you can draw, but that approximation will not give you a smooth curve, right? That smoothness will not be there because every data points you have some zigzag kind of curve.
Okay. Yeah, I'll test it. Thanks.
Yeah. Okay. So that's all from this sessions. We can meet tomorrow, and there we can start with different algorithms. We can start with k-means or other methods.
Sir, in day 2 we did regression.
Day 2, yeah, this is regression, right?
Yes, sir.
Yeah. So you can try out these things. One good practice will be to do regularization part by yourself. There will just adding your regularizer in your loss function, right? That you can try out and see how it works.
Okay, sir. Thank you.
Okay, so let's close the session and we'll move tomorrow. Okay, so
Thank you, sir.
everyone
Thank
for
you very much,
joining.
sir.
Thank you.
Sir, when will the assignment